Hi, and welcome back to Understanding Motors. Last episode, we started our journey into the practical aspects of using a motor by outlining some of the most important values to look for on a potential motor's datasheet. This week, we're going to jump into how to actually use your motor once you've acquired it and either attained or fabricated your circuitry to drive your current. Just a heads up, while I typically try to keep my videos relatively intuitive and accessible to people who haven't taken any advanced classes, this video will definitely contain some control theory ideas. This episode, we will be designing our control loop in two phases: the outer control loop, which will control the position or velocity of our motor system, and the nested current control loop, which won't apply to folks who purchased a prefabricated motor driver. So, without further ado, let's get into it. We're going to start this episode by taking a look at the mechanical system that is a motor driving some load. We're going to assume that the system will have some rotational inertia J and some viscous damping, which is linear with velocity and characterized by a damping constant B. For this second, we're going to assume that the rotational compliance between the driven load and the motor is negligible. From Newton's laws, we know that the inertia times the rotational acceleration of the load will be equal to the net torque supplied to it, where the net torque is the difference between the torque input via the motor and the losses due to damping. I'm going to denote our angular velocity as the first derivative of rotational position with respect to time. To make our notation simpler, we'll display this as a theta with a single dot above it. I'm going to refer to the angular acceleration as the second derivative of rotational angle with respect to time, which I will denote as a theta with two dots above it. By moving our damping to the left side of the equation, we can group terms such that one side is only a function of the derivatives of rotational position and the other is just our input torque. Now, to further analyze this system, we'll move it into the Laplace domain through the Laplace transform. Assuming no initial conditions and moving some terms around, we can get our transfer function from torque to position as having two real poles, one at the origin and one at negative b over j. Note that if our compliance in our system was not negligible, our transfer function would have an additional term k in the denominator, and depending on the size of this constant relative to our damping, the poles of this system may no longer be on the real axis, meaning that the system would have a tendency towards oscillation. So this transfer function describes our motor servo system and how it responds to an input torque, but we want to be able to control how it's oriented. So we're going to wrap this system in a feedback control loop. This loop will look at how our system is positioned, compare it to how we want the system to be positioned, and then apply an appropriate torque to drive the system to this desired orientation. The simplest feedback controller we could make is what's known as a proportional controller, with a gain Kp. This would apply a torque to the system which is proportional to the error between the desired position and the motor's actual position. Intuitively, you could think about this controller as connecting the rotor to the desired orientation through a virtual linear spring. For such a controller, our root locus for the system would look like this. Here, we would likely want to move this pole at the origin adequately far left so that the system responds quickly, but we most likely wouldn't want our poles to come off of the real axis, as this would mean our system is underdamped, and underdamped systems are often undesirable due to overshoot and potential for oscillation. Depending on what response we want out of our servo system, as well as the ratio of the motor's damping to its inertia, or in other words, the location of this pole, a simple proportional controller may work. However, if our system's damping is not large relative to its inertia, we might want to add a zero to the system by using a proportional derivative controller. Essentially, what this does is artificially increase the damping of the system. Returning to our analogy of a proportional controller as a spring, a proportional derivative, or PD controller, would be like making this connection with a spring damper pair. If we use such a controller, we see that our open loop transfer function between error and position is equal to KdS plus Kp divided by Js squared plus b times s, meaning our root locus would now look like this. Adding this zero via the damping controller will amplify high-frequency inputs to the system, which is generally not desired. However, since torque to position is a second-order system, it's almost never going to be an issue in position servos. However, if instead of position, we wanted to control the system's velocity, our motor model would change. Where before our system model was 1 over js squared plus b times s, it is now 1 over js plus b. If we were to use a PD controller on this new system, we have a couple of issues. First of all, if we do some algebra to solve for the error when using PD control to track velocity, we can see via the final value theorem that, for an input step response in our reference, we'll have a steady state error in our velocity tracking. To fix this, we could add an integral term to our controller, thus making this a proportional integral derivative, or PID controller. Looking at our final value theorem, this fixes the steady state tracking error. However, there can be another issue here in practice sometimes, having to do with this derivative term and system noise. Since our torque to velocity system is first order as compared to our second order torque to position controller, the added zero associated with the derivative control term can cause high frequency noise to be filtered out less. This is made worse by the fact that, in general, most servo systems sense position directly, then differentiate to get a velocity signal. This means that noise in your sensing will be amplified, potentially making your error term and the input to your controller quite noisy. This noise can be mitigated to some extent via digital filtering. However, as you add filters, you also add phase lag. For this reason, and for simplicity's sake, it's often better to ditch the derivative term and use a PI controller for tracking velocity. So, now we have a way to control our system's position or velocity via an input torque. But, as we talked about several episodes ago, we still have an issue. We don't have a way of directly dictating our motor's torque application. Instead, we're going to have to make a nested control loop which uses a value we can control, voltage duty cycle, to drive the current running through the system and thus control the torque. To design this controller, we're going to want to repeat our analysis from earlier, this time looking at the motor's electrical dynamics from a controls theory perspective. As we have said many times at this point, we know that the motor can be modeled as a resistor, an inductance, and a back EMF term. For right this second, we're going to ignore this back EMF term, as nonlinearities make control theory more difficult. So our simplified system can be described by the differential equation voltage equals Li dot plus Ri. Once again, taking this into the Laplace domain, our transfer function of voltage to current is thus 1 over Ls plus R. Now you may notice that this looks a lot like the torque to velocity system we just described. We have one real pole located at negative R over L. Looking at the root locus, we see that since we only have the one real pole, we could in theory just use a proportional controller here. And as we crank the gain up, this pole will shift left and our system will respond quickly. However, there's a few practical issues with this. First of all, the voltage we can supply will at some point saturate, and then we'll have a nonlinear system. Additionally, since, like most real control systems, this is a discrete system, not a continuous one, if the proportional gain is high enough or our sampling frequency is low enough, it can result in instability. Additionally, while constant current commands may not be the norm for servo motor control, we can see again via the final value theorem that, for a constant command, this control scheme would result in a non-zero steady state error, which would only be made worse by the back EMF term we're currently ignoring. So typically, the current control of a motor is done via a PI controller, where the zero is placed on top of the pole at negative R over L, effectively canceling its dynamics out. Obviously, perfectly canceling this pole isn't possible as the motor system changes with temperature, but placing the zero approximately on this pole generally works very well. This approach results in quick system responses with minimal dynamics, and if you're controlling for quasi-constant rotor velocities, this integral term will eliminate the issue of back EMF. However, if you're using a motor and a servo system where velocities aren't quasi-constant, we can still minimize this back EMF disturbance. We know from earlier episodes that back EMF is approximately the torque constant multiplied by the angular velocities, assuming you have your units in check. And it produces a voltage in the motor which resists the rotor's turning. With this knowledge and our ability to get a slightly noisy approximation of velocity from the motor's outer control loop, we can thus add in a feed-forward term which is a function of the rotation rate of our motor. In doing so, we can mitigate any issues that this back EMF term would cause in our controller. This often isn't necessary, but for some systems that are turning very quickly and non-constantly, it's a good approach if feedback control alone isn't producing adequate results. So that's the basics of designing your motor controllers. I'll put some links in the description below for additional resources on these topics, as well as some helpful tips for tuning the systems once you have them up and running. Next episode, we're going to look at how motors can operate as generators and how that can be used to run motors more efficiently. Thank you for watching, and I'll see you next time.